Okay, so, oops, sorry. Um, I want to go through one more example about like looking at differentiability at a point. So the last video we looked at proving, kind of very formally, there was a derivative at a point. It was continuous, so we knew it connected, but it connected smoothly, right? The derivatives matched. Here, it's not so much proving it; it's more of a solve or a find. And so, like, I really wanted to highlight that first. That it says find, or if it ever said solve for the values of a and b, like if that were the directions, then this is not a formal proof. So I don't have to be as conscientious of keeping those limits and making sure I'm accurately conveying that on a formal proof. So first thing, to guarantee it's continuous, we need the two pieces to line up. And so we've done that before. We did that last chapter. So I need ax plus 4 to equal bx squared minus 5, only when x is equal to 3, like when those two pieces line up. So that would be a 3a plus 4. Oh, there's the bell. Nice. Yeah, it's going to ring in 2 more minutes. 9b minus 5. And so, I could subtract the 4 across. So I get 3a is equal to 9b minus 9. And I could divide by 3, which actually is pretty nice. So a is equal to 3b minus 3. But that doesn't really get me anything in terms of a set of answers because it's only one equation written in 2 variables. So that doesn't guarantee it's going to be differentiable. Even if I choose a set of a, b that makes this true, doesn't guarantee that it's going to be differentiable. So what we have to then do is look at the piecewise derivatives. So kind of coming over here, I might say, okay, f prime of x is equal to, and think about this derivative, if this is linear, we know 4 is constant, so it goes away. The exponent of x was 1, so that's like 1 times a, or just a, if x is greater than 3. And then the derivative here would be 2b x to the first power if x is less than or equal to 3. And again, I'm going to go ahead and state that equality because I'm trying to make this differentiable. So I want it to be defined everywhere. So now I want a to equal 2bx. I want the derivatives to line up when x is equal to 3. So that really means that a is equal to 3 times 2, 6b. So this value of 6b is what I'm going to input here. So I'm going to get 6b is equal to 3b minus 3. Subtracting the 3b over, I get 3b is equal to negative 3, which implies that b equals negative 1. So there's our value of b. And then how do you get a? A is equal to negative 6. So those are your 2 values. And there's the bell. Now, if you wanted to check your work, you certainly can substitute it in. So, a being negative 6. So let's rewrite that function just to check it. So now f of x is equal to negative 6x plus 4 if x is greater than 3. And since b was negative 1, we get negative x squared minus 5 if x is less than or equal to 3. So substituting 3 from both sides, if I had to do like a rigorous proof here, putting a 3 there, showing limit from the left and the right, that's negative 18 plus 4 is negative 14. And then go to the thin red there. So we get negative 14, and then putting in 3 here, 3 squared is 9, but make it negative, subtract 5 is also negative 14. So we would know that it's continuous, and then the derivative, might as well check our work, is equal to negative 6 or negative 2x, depending if x is greater than 3 or if x is less than or equal to 3. And you can see that we both get negative 6, and it lines up perfectly. So yeah, I just wanted to do those 2, and I knew we would not have time in class to really go through. I didn't want to rush what we did in class. So pay attention. Is it a formal proof, or is it just a find or a solve, and then answer them appropriately? So, okay, very nice job. And then, as always, let me know if you have any particular questions.